Welcome to the Deep Dive, where we take your sources and cut through the noise to get straight to the critical insights.
Yeah.
Today we're getting into something really specialized, but incredibly important. It's about a material used right inside the human body. Amorphous fumed silica nanoparticles. These are found embedded in the shells of certain breast implants.
And the mission here is, frankly, urgent. We're pulling together some very complex toxicology studies and regulatory documents to understand something pretty fundamental. Why is an ingredient that was, presumed safe for decades now being linked by scientists to chronic inflammation and really serious systemic diseases?
It sounds like you have some serious evidence.
We do. We have solid evidence about the intrinsic molecular level toxicity of this specific kind of silica. We have quantitative proof that the implant shells actually degrade and release it. And we have an appeal to regulators that highlights some pretty significant historical oversights.
And we're talking about particles that are just unbelievably tiny, right? Something like 5 to 7 nanometers.
Vanishingly small. To give you some scale, that's about 15,000 times smaller than the width of a single human hair.
Yet they make up a huge part of the implant shell, up to 27% of its thickness. So I guess the core question we're tackling today is this. Does this specific nanomaterial, once it's exposed inside the body, create a kind of biological perfect storm? Okay, let's unpack this. Let's start with the basic toxicity of the material itself.
Right. So the main finding, and this comes from work by researchers like Zhang and others, is a really crucial distinction. Not all amorphous silica is the same. I mean, not even close.
Okay.
When we talk about toxicity, it's not just determined by the chemical formula, cyanoeros. It's critically determined by the production method.
How it's made.
How it's made.
Yeah.
That dictates everything about how it interacts with our cells.
So the manufacturing process is actually more important than the basic chemistry.
That's
a fascinating idea.
Yeah. So the research compares two main types, right?
It does. First, you have what's called colloidal silica. You can think of this as the safe version.
It's made at low temperatures in a solution. It's like it's cooked slowly and gently. The result is that it forms these relaxed, large molecular rings. When it's introduced to cells, the body can handle it. It's internalized, processed. It's like a smooth pebble the cell can digest.
And then there's the other kind, the one used in these implant shells.
Yeah.
Pyrogenic silica.
Exactly. Also called fumed silica, or by its trade name, aerosol. And this is where the trouble starts. This stuff is made using something called flame pyrolysis at incredibly high temperatures. We're talking 1,200 to 1,400 degrees Celsius.
Wow.
And then it's flash-cooled, a rapid thermal quench. This violent, high-speed process is the entire source of the problem.
Okay, so this is where it gets really interesting. Because of that rapid cooling, its molecular structure gets physically strained. I read that it has these things called strained three-membered rings, or 3MRs, kind of frozen into a structure.
Right.
What are those, and why do they make it toxic?
That's the perfect question. Think of the silica as a complex lattice of rings. Most of those rings are stable, with 4 or more members. A 3-membered ring, a 3MR, is forced into this extremely tight, angular shape. It's like trying to force a triangle where a square should be. There's this immense structural tension just baked into the nanoparticle.
So it's fundamentally unstable.
Highly unstable. And that's the key. When these strained rings encounter biological fluid, like inside the body, they can literally break open.
And when they break?
They generate their own ammunition. They produce reactive oxygen species, ROS, specifically these highly damaging hydroxyl radicals. This is what causes oxidative stress, and that leads directly to dose-dependent cell death and something called hemolysis, where your red blood cells actually start leaking.
Hold on. Are you saying that the heat from the manufacturing process is what makes it toxic? That the process itself permanently programmed this material to generate free radicals?
That's a perfect way to put it, yes. And it gets worse because of its physical shape. Pyrogenic silica forms these stiff, fused, chain-like aggregates. Imagine like tangled metal fencing.
So it's not a smooth pebble that the cell can just absorb.
Not at all. These rigid chains get stuck to the outside of the cell membranes. They can't get in.
And that external contact is the trigger, isn't it? The cell can't process it, so it just sees it as a constant external threat.
It does. And this continuous molecular irritation is what triggers a massive immune alarm system called the NELP3 inflammasome.
The NELP3 inflammasome. Let's translate that. What is it?
It's essentially the immune system's master panic button. When it gets activated, it floods the area with pro-inflammatory signals, mainly a cytokine called IL-1.
And because that rigid silica particle is stuck on the outside of the cell.
It's pressing that panic button nonstop. You get chronic, self-sustaining inflammation. That's the core mechanism that explains this intrinsic and really unusual toxicity.
Okay, that's a very clear picture of why the material itself is so problematic. But in the implant shell, it's initially coated, right? This brings us to the next part, the degradation time bomb. The silica is passivated with a trimethylsyl, or TMS, coating. This is supposed to mask those reactive groups.
It is, and that's the critical regulatory gap everyone is pointing to now. The coating was seen as good enough to prevent an immediate reaction, but it was never designed to last forever. It's a temporary chemical patch in what is a very aggressive, very wet, very mechanical environment inside the body.
So what's the evidence that this so-called protective barrier actually fails?
Well, we have direct measurable proof. There was a study in 2015 on retrieved implants that reported an average reduction of 16% in the thickness of the implant shell after just 51 months.
That's only a little over 4 years.
Just over 4 years. And anecdotally, clinicians have reported cases where the entire shell seems to have, well, dissolved. This breakdown of the main silicone matrix proves the TMS coating is failing. It's oxidizing, it's hydrolyzing, it's gone.
Which means, when that coating degrades, the patient is exposed to not one, but two different problematic substances. This is the perfect storm you mentioned.
Absolutely. The first exposure is to the pyrogenic silica core itself, now unmasked. It immediately starts activating that NALP3 inflammasome pathway and generating those damaging free radicals.
And the second exposure?
The second exposure comes from the degradation byproduct of the coating itself, which is trimethylsilinol, or TMS-IOH.
And what's really terrifying here is the self-reinforcing nature of this. The body's own immune response actually speeds up the problem.
It does. A chronic inflammatory environment is biologically aggressive. You have acidic pH, you have hydrolytic enzymes, you have free radicals being pumped out by immune cells.
Oh.
This whole soup just chews away at that TMS coating even faster.
It's a devastating feedback loop. So, more inflammation leads to faster breakdown.
Which releases more reactive silica.
Which creates even more inflammation. It just spirals. A vicious circle.
Precisely. And the TMS-IOH, the byproduct, adds its own layer to the problem. It's a volatile organic compound that can circulate systemically. The thinking is that it can act as an adjuvant.
Meaning it doesn't cause the problem on its own, but it fans the flames?
Exactly. It can aggressively ramp up the immune system's response, potentially contributing to those complex autoimmune-like symptoms people report in what's known as ESA syndrome.
Let's move on and talk about size, the sheer risk of the size. Once these nanoparticles are free, what does being only 5 to 7 nanometers big mean for systemic risk?
The size is absolutely critical. It governs mobility. Particles this small can easily penetrate cell membranes. And, more worryingly, they can potentially cross major biological barriers that are there to protect our most delicate organs. The blood-brain barrier, the placenta.
So this isn't just a localized problem around the implant. This could be systemic.
It opens the door to systemic damage. And the research shows this has consequences way beyond just inflammation. These particles are considered genotoxic.
Genotoxic, meaning they can actually interact with and damage our DNA.
Yes. Studies show that silicon nanoparticles under 70 nanometers, and remember these are 10 times smaller than that, can cause DNA breaks and mutations. And they can trigger something called epigenetic changes. They can alter how your genes are expressed without even changing the DNA code itself.
So long-term cellular programming errors combined with chronic low-dose exposure to a DNA-damaging agent. I can see why long-term safety is under such intense scrutiny now.
And this provides the fundamental link to the growing clinical concern about BIA-ALCL, that's the breast implant-associated lymphoma.
Right.
Chronic inflammation is the undisputed driver for that cancer. So the continuous release of these highly reactive, NALP3-activating genotoxic particles creates the exact potent environment needed for that kind of malignant transformation.
What's really striking here is that the evidence for all of this, the migration, the systemic exposure, it may have been sitting in the scientific literature for decades, but it was just misinterpreted.
Completely misinterpreted. If you look at older studies on so-called gel bleed, researchers used powerful microscopes combined with a technique called EDX, which lets you map out which chemical elements are present.
And they kept finding the element, silicium, Si, in the scar tissue that forms around the implant.
That's the smoking gun location, right where the inflammation is happening. But here's the massive historical oversight. They just attributed that silicium signal to the silicone polymer itself. They said, oh, silicone has Si in it. That's all this is. They assumed it was benign.
They fell victim to confirmation bias. They saw silicon and just stopped looking. They didn't ask the next logical question.
Exactly. They failed to ask, is this silicon from the organic flexible polymer, or is it from the inorganic, rigid, toxic silica filler?
How would they have known the difference?
They would have just needed to analyze the carbon signature. A strong silicon signal with a weak carbon signal points directly to the inorganic nanoparticles. The failure to make that simple distinction meant the migration of the toxic filler was right there in the evidence for years, but it went completely unrecognized.
Wow. So moving on, this overwhelming new body of evidence led a Dutch patient organization, Stichting SVS, to take some pretty extraordinary action.
They did. They sent a formal, incredibly detailed letter to the US FDA requesting an urgent reassessment of these materials. And their request centers on rectifying a critical historical omission in the foundational 1999 Institute of Medicine Safety Report, a report that is, by the way, still heavily cited today as proof of safety.
And the patient group's point was that the report, it basically failed to properly read its own sources.
That's precisely it. Stichting SVS showed that the very document the IOM referenced, an old document from 1981, actually contained data showing that fumed silica could be just as toxic to immune cells as crystalline silica.
Which is a known carcinogen.
A known carcinogen. The difference between harmless silica and highly reactive fumed silica was known back then. It was just ignored or miscategorized in that pivotal safety assessment. It's a massive oversight that needs to be publicly corrected.
And they also highlighted a huge research vacuum, right? Out of thousands of breast implant studies, almost none of them even mentioned silica.
Fewer than 60. And shockingly, only a couple address fumed silica directly. And one of those, back in 1991, identified fumed silica as the most toxic component of the entire implant. The warnings were there, they were just systematically dismissed.
So this brings us to the core urgency here. The patient group asked the FDA to update the old report, to start new independent research, and to give clear information to patients. So what has the response been?
And that right there is the most frustrating conclusion to this whole story. The patient organization didn't just send this to the FDA, they sent it to equivalent authorities and regulatory bodies all across Europe. And despite the incredibly detailed, cross-referenced evidence of toxicity and migration, there has been a profound silence. We have not seen a substantive public response that acknowledges this new toxicological analysis.
So no official update, no call for the independent study that is so clearly needed.
Nothing. And that's what underscores the urgency. We have a scientifically sound case detailing intrinsic toxicity, quantifiable degradation, and documented regulatory failure, all compiled by patient advocates, and we are just waiting for authorities and the industry to officially acknowledge that this safety gap even exists.
The scientific data is there. It strongly supports the idea that the breakdown of these shells creates a chronic exposure route to these potent nanoparticles.
The question for policymakers isn't whether the evidence exists. It does. The question is how quickly they're going to act on it, especially when it seems like the evidence was there all along, just misinterpreted. The lack of a clear response so far only makes this more concerning.
We've traced a clear and frankly disturbing path today. High-heat manufacturing creates an intrinsically toxic material. The body's own environment breaks down its protective coating, and the release of these tiny, rigid, genotoxic particles drives chronic inflammation that can lead to severe systemic issues, including cancer.
And I think this deep dive really highlights a profound difficulty in our current safety systems. A lot of these materials were assessed decades ago using old standards that completely miss the unique physics of nanoparticles and long-term degradation. When a material is used for decades under a mistaken assumption of safety, the regulatory response really has to be rapid and comprehensive once the new science emerges.
So what does all of this mean for you, the listener? This whole story forces us to consider that materials we've long deemed safe, based on old, incomplete science, may actually pose a delayed cumulative hazard. And the provocative thought I want to leave you with is this. How many other materials currently implanted in the human body are relying on these kinds of outdated toxicological assumptions? And what unseen costs are we accruing while the regulatory system struggles to catch up to the science of the nanoscale? That knowledge gap requires immediate, focused research, especially when patient health is on the line.